This is AE 597 with Professor Krishnamachari on Wednesday, June 29, 2016.
So, last class we were talking about medium access. And on the topic of medium access, there's broadly two classes of techniques. There's randomized access and there's scheduled access. And the things we talked about so far, like slotted aloha and CSMA, fall into this category, while scheduled access refers to things that involve, for example, time division, multiple access, or channelized protocols. And the key difference is that with randomized access, your nodes can transmit whenever they have data with some probabilities. But with scheduled access, they are sort of pre-allocated time slots on which to do the transmission. So just to kind of recall what we covered with respect to these two, for slotted aloha, we found that sort of the maximum throughput is achieved if the probability is 1 over n, and then the throughput you get basically tends to 1 over e, which is roughly 36-37%. Right. And then we talked about throughput regions for multiple users. With sort of different access probability. And the main takeaway from the analysis there was that at the boundary, the summation of the pi star must equal 1, and the corresponding throughput that the ith user would get would just be pi times the product of I and j not equal to I of 1 minus pj. Okay. So then the other type of randomized medium access that's very common in wireless networks is CSMA. And here we have a much more sort of complicated expression for the throughput, but really what it boiled down to for PCSMA, sometimes called P persistent CSMA, where contention slots delta are smaller than collision time slots, which are smaller than the success time slots. And in this case, the throughput becomes the success time slot times the probability of success. So for the general case, you have n ways in which this could happen, divided by delta times nobody transmits, plus the same expression here, plus collision with probability 1 minus those. Then we talked about the 802.11 CSMA, and it's a little bit more complicated because the contentions are not like independent probabilities P that are chosen, but we basically think of it as a finite state machine describing the back-off stage and counter value. And the way the analysis by Bianchi goes, you then take this Markov chain that you get, so basically modeled as Markov chain, and the net result of that Markov chain are probabilities which kind of go into an equation similar to this one. Okay, so basically gets eventually treated by the same throughput model. Right, so there's some, so you have to derive the steady state probabilities. Okay, then approximate as CSMA. So that's really the crux of that whole model. At the end of this model, you derive what the throughput looks like, and if you remember the Bianchi paper, when you look at the throughput versus numbers of users, you'll find that the throughput is a lot better than 37%. And even from this equation, you can kind of see that if delta was really small and TC was kind of small and TS kind of dominated, that would make this ratio get closer and closer to 1 if I make TS really, really large compared to delta and TC. So intuitively, for larger packets, CSMA throughput can be high, right, 90% or more. And that's really why we use CSMA. It's pretty amazing that you have a protocol where the nodes haven't been told when to transmit, but they're coordinating purely by listening to make sure they don't transmit when another node is transmitting in such a way that they're getting close to 90% utilization. But the key insight is that whenever they win the contention, you're assured that you won't cause any more collisions. And if when you win the contention, you're going to occupy the channel for a long time, that's how you get the efficiency. That's the key idea for how CSMA gets efficiency. In slotted aloha, we can't do that because every slot is the same duration. So whether you contend or not, you're wasting the same amount of time. So if your packets are large, your contention slots are also large. So you don't get the efficiency benefits. Right? Or if your packets were larger than contention slots, but you were not doing channel sensing, then you would start sending while somebody's sending a packet and you would cause collision. So to prevent that, you have to make the slots large enough, right? Because you don't have the ability to sense the channel. So in some sense, slotted aloha seems doomed to have poor efficiency so long as you can't sense the carrier. And in general, slotted aloha is almost never used these days because of the higher efficiencies we get with CSMA. So all of the 802.11 systems which use randomized access run CSMA. They don't use slotted aloha. Oddly, though, there are protocols that are still running slotted aloha, and one of the most widely used protocol that still uses slotted aloha, believe it or not, is the cellular network. So in a cellular network, there are two kinds of channels. There are data channels and there are control channels. And in cellular networks, there's a random access channel called, just called RACH. So this is a kind of a control channel, control signaling channel. And it's basically slotted aloha. Okay, There's some specific details in it. So this channel is really used to signal to the cellular that your phone has data to send. And it's not actually used to send the data. It's more to tell this base station that you need resources to be able to communicate your data. So it's just used for the control signaling. So once the base station gets to hear that these nodes need the data channels, it goes ahead and allocates the data channels, and then from that point on, things are scheduled. But during that random access period, they tend to communicate with the base station using slotted aloha, and there isn't a listen before send, there's just a send. Okay. And so there's speculation that one of the reasons why when, for example, a lot of smartphones started to take off, the cellular providers found that they were seeing a lot of problems on their networks. And the speculation was that the problem wasn't that they didn't have adequate data bandwidth. The problem was that their control channels were getting overwhelmed by control signals. Because now your mobile apps are not just making phone calls once in a while, they're constantly sending short bursts of data. And when, at the very early stages when things were sort of poorly configured, they were spending a lot of time on the control channel, which if it was based on slotted aloha, would not be as efficient, and they didn't allocate enough control bandwidth to give you the performance that you needed. So I think they solved the problem by provisioning the control channels adequately afterwards, but in the early days that ended up being actually a source of challenge for them. So last spring, I was visiting Texas A&M, and there was a faculty member there, Krishnamachari, who told me about work that he has been doing fairly recently, about 2012 is when their paper goes back to, on improving the performance of slotted aloha by exploiting new physical layer and coding capabilities. And so I wanted to spend a few minutes kind of talking about this new protocol that they came up with, a new idea, which shows that even without CSMA, basically using slotted aloha, we can drive that efficiency from 36% to close to 100%. But it leverages a different physical layer capability that doesn't really exist today, but that's emerging. So let me describe their work. It's somewhat theoretical. There are no real implementations of their protocol that I'm aware of. In fact, that's one of the open research problems these days is, can we implement their version? But the beauty of their scheme is that if you can get it to work, you don't need even carrier sense. You can have just transmitters that are unable to sense the channel that are able to achieve very high throughputs. But what it requires is for the receiver to have a greater capability to decode packets using something called successive interference cancellation. So could I please have the computer over here projected? Okay, and also on the screen for remote viewers. Okay. Yeah. So this is the paper that he told me about. This is a paper from 2012. I will post it on our course website so you'll all have access to read it more carefully. So the title of the paper says it's an iterative collision resolution. It is about iterative collision resolution for slotted aloha, an optimal uncoordinated transmission policy. So let me kind of describe their problem, and you'll see how it matches exactly the kind of things we've been talking about. So they're talking about a multi-user system with K users in which every user wishes to transmit one packet of information to a central receiver. So you have these K receivers, they're all transmitting to the same base station. And the one subtle difference is that now they are assuming that the total time for communication has been split into a number of time slots. So we're going to have m different time slots, and each time slot is as long as you need to send a packet. That's typical in slotted aloha. And the idea is that in any given time slot, there may be multiple users that will send their packets. Right now, for slotted aloha, our assumption was that if there's more than one user that sends a packet at the same time, it's going to be a collision. So this is the assumption they want to relax. So they want somehow to be able to decode packets even when there are multiple senders sending the information. So a reasonable question to ask is, why might you be able to decode, like for example, if two users send a packet at the same time, under what conditions is it reasonable to assume that you can actually decode the reception at the base station? And they use a physical layer idea that sometimes is referred to as successive interference cancellation. Here they refer to as iterative interference cancellation. The basic idea is that if I'm getting two packets from two users, but I already know the content of one of those packets, maybe because I've already received it before, then I can somehow subtract out the known packet from this signal, or the interference from that known sender from the signal, and I can then focus on just decoding the remaining user signal. Does that make sense? So if of course, if I had not heard either of their messages and I hear a jumble of their messages, there's no way for me to decode. But if I know one of the messages already, and there are two messages now, right, the claim is that I'll be able to decode the other message. Now, this is a strong claim. It is something that theoretically is possible. There are some very simple proof of concepts that people have done in theory, but real radios that can do that don't really exist today. Okay, so that's the sense in which this is kind of a more futuristic concept. But it's not unreasonable even theoretically. So just bear with me, set aside like what the circuits might look like, but just conceptually what might that look like? So you have two signals that are coming to you. One of the signals is for a packet you've already decoded, which means that you know exactly what the signal should look like. Okay. If there was no distortion in the channel, assume that there was a certain attenuation of the signal, and you know the attenuation, so you know the channel gain from that user. So you know exactly what you're receiving is the sum of two waveforms, and one of those waveforms is known to you, like even the attenuation level is known to you. So in theory then, you can take the combined waveform and just subtract from it the known waveform. Then what you're left with is what you would receive if this interfering node had not even sent the message at all, right? So that's just like decoding one message. And if you're able to do that, then you've got, in this time slot, even though there are two packets being sent, you're able to decode the other one if you've already known it. So this is the assumption they make in this paper. So one assumption they make, and this is also a strong assumption, is that the receiver knows the exact set of users who transmit during every time slot. So this assumption says that not only are they, when they get that combined waveform, they also know whose waveforms got combined together. Right? Not just that they are combined, that they know one of them, but they also know exactly who the users are, who the two users are. And there are ways to get around it. Worst case, you can try exponentially many combinations of users and find for which one it works. But this is also one assumption in this work. So the way in which the users are going to choose to transmit is that the kth user is going to generate a random variable. And the random variable comes from some distribution. And based on this distribution, it's going to choose a certain number of time slots, dk time slots. So it generates this random variable dk, so it's a number from 1 to m. So you have m time slots. You pick a number from 1 to m. And what's the probability with which you pick 1? What's the probability with which you pick 2, 3, 4, 5? That's predefined. There's some probability distribution function from which you draw that number. Okay? You draw this number. So let's take an example. Let's say capital M is 10, and the number you drew was 4. So what it's going to do is, from the set of 10 slots, it's going to pick 4 uniformly at random. Right? So you pick, one way to do that would be you first randomly pick one number from 1 to 10 uniformly. Then, having taken that channel out, from the remaining 9 channels, you pick randomly, uniformly one other channel, and so on, until you take 4 channels that are uniformly chosen. Now, this is what the user is going to do. It's going to go ahead and transmit on those slots. Okay? And at the receiver end, what the receiver is going to do is the following. It looks at the data received in all M slots. The assumption they make is that you already know for each slot which user was transmitting at each slot. And the first thing the receiver does is that, so there may be some slots in which nobody sent. So those would be idle slots, you can't do anything. There will be some slots in which exactly one user would have sent a packet. It's possible because they all chose independently the number of slots to send at. It's possible that there will be some slot in which there is just one user. Okay. If there is one such slot, you go ahead and you decode that packet, because on that slot, even from standard slotted aloha, we know it would be successful. But now this is where their algorithm gets interesting. So now what you do is, on every slot in which this user sent, which you know, that's an assumption they make, you can go ahead and subtract out this user signal. Okay? So now think of all of those transmission slots. All of the slots that are empty, you've already ruled out. All of the slots in which there was one user sending, you've been able to decode. But more than that, you've reduced the remaining slots, which would normally in slotted aloha have been a collision. You've kind of simplified for those slots. You've removed some of the signals. Some of the interfering signals are gone. Okay? So now you look at what remains. And now the question is, are there any remaining slots in which there's only one sender sending after you've subtracted out the ones you've already decoded? Right? If there's any such slots, you can remove those as well. Not only from that slot, but from any other slot in which they show up. And then you repeat this process. So in other words, you iteratively go through the set of M slots and you try to remove any packet that shows up in a single slot you're able to decode, and then you're able to subtract it from the other slots. Okay? And so if you can do that and you can iterate, eventually you'll clear out a certain number of slots. Okay? The main result of this paper is really fascinating. What they show is, as you increase the as you increase the number of users k and increase the number of slots m, so the ratio k over m is something they call eta, which is the actually, so let me take even a step back further. So if you think about it sort of intuitively, the larger the m is, the more likely you are to be able to decode all the users. If m is sufficiently large, the total number of time frames in which they were transmitting is sufficiently large compared to the number of users, then I can have a higher probability that the users pick a different channel, right? And so I'll be able to decode all of the users. So intuitively, m being large means that you're able to decode all of the users. But in general, there'll be some m for a given number of k at which you're able to decode all of the users. Okay? And so this ratio k over m is what they're going to call the throughput, because m is the total number of slots and you're trying to decode k users out of it. K over m is your throughput efficiency. What they're able to show is that as k gets larger, as the number of users get larger, you're able to take this ratio of k over m and get it to be arbitrarily close to 1, which is the throughput approaching 100%, as the number of users grows. And moreover, in order to do this, so the only degree of freedom we have in their protocol, if you think about it for a second, so in slotted aloha, the degree of freedom you have is p, the probability with which you send a packet, right? In their protocol, the only degree of freedom you have is the distribution with which you choose to send how many of the m slots should you try to grab, right? Because once you pick from that distribution a random number, then the rest of it is kind of out of your control. You kind of uniformly choose that many slots to transmit at, and then the receiver decodes. So the only degree of freedom to optimize the performance of this iterative interference cancellation version of slotted aloha is how do you choose that initial distribution. So what this paper shows is that there is a well-known distribution known as a soliton distribution. And let me see where it says that here. There's something called a soliton distribution. And this paper shows that the optimal distribution for this problem is the dual of that well-known distribution. And using that distribution to choose the number of slots, one can get arbitrarily close to the upper bound of 1. So in the paper, they actually, let's see if they give the, they didn't show actually even a plot where they evaluate this as a function of number of users. Yeah, I'm not seeing that expression explicitly here. I'll just say a little bit more. I will put up this paper for people to look at. So they kind of think of any realization of this protocol as a bipartite graph where the nodes on the left are the users, the nodes on the right are time slots. And so when they choose particular time slots to transmit at, what might happen, for example, is maybe users 2 and 3 transmitted at time slot 1, user 1 transmitted at time slot 2, user 2 transmitted at time slot 4, and so on, right? So these probability distributions from which they're choosing time slots are basically related to what's called the degree distribution. So from each node, how many edges go out, that's the number of slots that they picked. That's the thing that you're drawing from the distribution, right? So the degree distribution for these vertices is exactly the distribution that you're trying to optimize, okay? And they present the, so L of X is what they're calling the node degree distribution, and they give some expression for this distribution here that they prove under certain conditions, how the efficiency of the system is directly related to that distribution, and the fact that it ends up becoming a function of a parameter that as it goes to infinity, you end up with the efficiency approaching 1. So basically, by choosing this distribution, the probability of how many edges will go out of each node carefully, they're able to optimize the throughput of the system and show that as the number of users grows, it's going to approach 100%. The reason I presented this work is sort of twofold. One is to point out that, you know, even though slotted aloha has been around forever, literally going back to the very first wireless communication systems in 1972 in the University of Hawaii, and CSMA, which we use in 802.11, has been around at least since the 80s, and we've been, you know, using them in wireless local area networks in 802.11 since the 90s. By no means are we at the end of developing new randomized access protocols. And here's an example of a protocol that doesn't even require carrier sense, but promises to give you close to 100% throughput, or at least very high throughput. But the trade-off is that in order to implement these new ideas, we're also going to have to make some advances in the decoding side of things. So maybe the complexity of the decoder at the receiver is going to be higher. So those are things that people are working to implement. But I just wanted to throw this out as an example of how knowledge in our field is not something that's constant, that you learn about in college and then you'll be done for the rest of your life. These are developments that are happening continually. One reason we don't even have a textbook for this class is every year as I teach the class, new developments show up that I want to put in as part of the course. And so it's really, I would go so far as to say that we're very much in the midst of developments in wireless communication still. Right? So a lot of people think that, well, cellular has been around since the 80s and 90s, so there must not be a lot of new things to do in the field, but there's a lot of developments all the way down to the physical layer that are still being developed. Another idea that we didn't talk about, but that's been happening over the last couple of years, is this idea of multi-user MIMO, in which not only are you getting the MIMO benefits of throughput, you're actually allowing that to come for completely different links, not just for the same source destination link, but for multiple user or multiple links simultaneously in a network. And that's an idea that, for example, promises that if you have, like today, if you have 10 links that need to share a spectrum, unless you can get a power control solution that allows all of them to be in the same spectrum at the same time, you're forced to divide your throughput by a factor of 10. So if you have 10 users in an area, they're all sharing the same spectrum, they would have to get only 1/10. But with this multi-user MIMO, in principle, they could all get a full 100% of the throughput. And so that, I mean, that's a completely different level of gains, even beyond what we're describing here. This is not just 100% throughput where the total spectrum is being shared by the users. It's actually every user gets the entire bandwidth, right? So people are talking about schemes like multi-user MIMO, interference alignment, and so on, that are still very much in the theory stages. And as we figure out how to develop real systems with them, we'll get dramatically higher throughputs in our wireless network. So I put this out there as an example of something that goes well beyond what's very well understood, already developed. Okay. So can I go back to the overhead camera, please? So I'll put up that paper, take a look. It's not so much that it's a state-of-the-art, existing scheme, but it's sort of an idea of what's coming in the future. Okay. So, so I said that besides randomized access, the other type of mechanism is scheduled access. And this shows up a lot in channelized systems where the channel could be time, it could be frequency, or in the case of, say, CDMA, it could be codes. Right, so if you remember, CDMA is basically direct sequence spread spectrum in which different links are getting different codes. And if they're truly orthogonal, they may be able to offer that code to different users. And so the key idea is that all of these are meant to be somehow orthogonal dimensions. Right, so ideally, no interference. And sometimes the problem of doing channel allocation is really, really simple. There's not a lot of complexity associated with it. So, for example, if I had an access point and I have a set of users, and of course these users don't have to be humans with laptops or mobile phones. They could be machines that are generating sensor data that need to be sampled at a certain frequency. So particularly for many applications, for example, industrial sensing, have very predictable traffic. So a simple example might be sensors deployed in some industrial plant that are measuring some chemical concentration, are measuring temperature values at different parts of the plant, and you just have a regular schedule. Like once every second, you need to know what the sensor is reading. Once every minute, you need to know what the sensor is reading. So this is an environment in which there's no uncertainty about when the data gets generated. It's not that they have data all the time. Things are very periodic. Another very good example is automated meter reading, sometimes called AMR, which shows up for parking meters, for example. So a lot of cities are starting to deploy wirelessly equipped sensors on the parking spots, and when somebody puts in money or feeds the meter, the information about how much time is remaining, all of this is being just broadcast wirelessly. And there may be a set of meters that are broadcasting this information at some granularity. You don't need that information very frequently. Right? Even on a city street, if every meter was giving you that information once a minute, probably that's enough. And whoever is doing the traffic enforcement just needs an information that's updated to within a minute of saying on this street who has stayed too long on their meter. And I don't know about you, but if you've been in West Hollywood in particular, I think it was West Hollywood and I think maybe even Culver City, there are cities where it feels like you are over by 1 minute and you get a ticket on your windshield. And part of the reason why that is growing is that many of them have started deploying automated meter reading wireless devices. So it's not that they're driving by staring at the green light blinking. They're simply getting a notification on their phone that these particular spots have overstayed. And so the point here being it's a very, very deterministic, very periodic type of traffic. Right? So for an application like this, CSMA actually doesn't even make sense. There's no reason for all of these meters to contend for when they should access the channel. There's no reason in an industrial plant where you have a fixed schedule of sensing for all of the nodes to have randomized access as their way of figuring out when to send the packet. So if you know the periodicity with which you need to send the data, you can just schedule the transmissions for each of them, and you can say at this particular time slot, it's this node's turn to send. At this time slot, it's this node's turn to send. So basically, with synchronization, right, and this is important that all of the nodes know what time slot it is. And so long as you have that synchronization, nodes can be pre-allocated a time slot. Right. And so, the first, whatever that time slot is, goes to this user, then to this user, then to this user. So in the application we talked about for city streets and parking meters, it would be very natural to implement a TDMA-based schedule rather than to use 802.11 like CSMA. Okay. So again, the MAC protocols are not a one-size-fits-all solution. If there are applications where the traffic is very deterministic, you probably want to take something like this. So in a simple setting like this, it's not even a complicated problem. You can just see, how to do it. Right? You just allocate everybody a different time slot. Channelization shows up in other settings as well. So, for example, classic cellular. Okay, maybe let me say in sort of an ideal cellular. So if you've ever seen these pictures of cellular, and in fact they go back to some of the earliest drawings of cellular systems, you'll see that they're typically drawn as hexagonal cells. Anyone know why they're drawn as hexagonal cells? Like what's interesting about hexagonal cells? It covers the entire area. It's a tessellation, right? So equidistant from the. So there's sort of this. It's a very symmetric tessellation. In fact, it turns out there's only 3 polygons: the triangle, the square, and a hexagon that can tessellate a plane. So the only things you could draw that will just tile perfectly are either triangles, right, things like this, or you can do them with squares, obviously, right? That's just your standard thing, or a hexagon. It turns out there's absolutely no other polygon that can tessellate. And circles, if you thought that the communication range of a base station is a perfect circle, does not tessellate. If you had to try and tessellate, you'll end up with all these gaps in the middle. Right? And so in some sense, the hexagon is the closest approximation to a regular symmetric structure that tessellates. So just... Well, that's true even for a square. So even for a square, you would have the distances to these 4. Okay, true. Is that true for a... Yeah, I guess that's true. So you're saying it's basically these distances are all the same. But really, this is just an ideal model. There's no real cellular system in which the cell is exactly a hexagon. So this is more of a mathematical convenience. It's a way to think about it. But even in this sort of ideal system, where kind of channelization shows up, and I'm just extending this out a little bit, is that one way to think about, here what we're doing is we're giving everybody a different channel. In this case, it was a different time channel. The way cellular came about, and the reason we even call it cellular, is to distinguish it from what used to precede it. And a lot of people don't realize that the first mobile phones, car phones, existed back in the 40s and the 50s. In fact, in Manhattan, you could sit in a car and talk to people on the phone back in the 50s and 60s. The difference between that system and cellular was that there was exactly one base station for all of Manhattan. And the number of people who could afford that phone was also very small. Right? So if your phone costs $10,000 a month, it's for the richest of the rich, and you only need one base station for the entire city. Right? And so it was a very different system, but the system didn't really scale. So you could not support more than, I don't know, 100 odd users in the city. Right? And so the idea of having wireless communications, that's not a new idea. In fact, back in World War II, we even had multi-hop communications, right? And we had even digital relays and so on. So, but the key idea that made it novel and interesting that people in Bell Labs in the 70s came up with, when they came up with the cellular concept, is the idea of frequency reuse. Okay. It's the fact that, if I have a certain amount of bandwidth, the problem with the whole area being the bandwidth is not enough users. I break it up into different cells. If I give the same set of frequencies to all of the neighboring cells, that's not good because they'll start to interfere with each other. So the idea is that you define some set of channels that you assign to each cell in such a way that neighboring cells have a different set of channels. If I could successfully do that, I can reuse the same channels but a certain distance away. Okay. And now I have this portion of the spectrum that doesn't interfere with nearby cells and gets reused. Okay. So to give you a concrete example, if I break up my spectrum into chunks of 3, for example. Okay, so I have a certain number of channels. I call them my A channels, my B channels, my C channels. I can then label this tessellation in such a way that we don't allow neighbors of the same cell to have the same. So let's see if we can figure it out in this case. So let me label this one as an A channel. And let's take this 3. So take B and C. So the type of structure we're trying to put together, this cell cannot be either B or A because then it would interfere. Cannot be C or A, so this would have to be a B. This would have to be a C. This would have to be a B. This would have to be C. This would have to be A, B, A, and so on. So you can keep on going in every direction, and you can show that in this way of allocating the channels, we've made sure that no two neighboring cells have the same set of channels, right? And it's allowing me to reuse the same set of frequencies a certain distance away. Okay. And of course, this is not the only way in which I could have broken it. If I want these to be spaced apart even farther, a more, let's say, a different way in which we could break up our total spectrum would be to break it up into 7 pieces. And then we get a reuse factor where the nodes or the cells with the same frequency would be even farther away. They would actually be about this far away from each other. Okay. So, depending on how you do this, you can have different reuse factors, but the key idea that's being enabled here is that by ensuring that neighboring cells don't have the same channels, okay, but far away cells. So this far away, of course, needs to be defined depending on the application, but far away cells can reuse frequencies. Okay? And by being able to reuse frequencies, we've now allowed our cellular system to support many more users. So now if this is Manhattan, if my cell sizes are sufficiently small, I can have hundreds of these cells in the city, and each cell is getting sort of 1/3 in this example, and you're reusing the same spectrum in multiple places. You can scale up your number of users. Okay. In fact, modern cellular systems go even a step further. In addition to breaking things up this way, they also do something called sectoring. So the idea with sectoring is that your base stations, in fact, if you ever look at city base stations, you can clearly see what that sectoring looks like. So you might see they have sort of this triangular kind of shape. If you look at a base station, each one of the sides of the triangle has a set of transceivers that's directionally pointing at a portion of the So for example, maybe it has kind of, this is 4, I should do 2. So if I take a hexagon, I can have a sectored antenna, and if it's only transmitting in this direction, what I can do is I can use the same set of channels that are used here in even a neighboring cell, so long as the direction in which this is facing won't interfere in the other direction. Right? So that improves the reuse further. So, the sector ones are actually, it's even at the, let me show an example. Sectorized cellular. See if I can bring up an image. I think this is an example. Let's take a look. Oh, could I have you switch to the desktop here, please? So here's an image of what sectorization might look like. So here are the 3 sectors. So it is the base station in the middle, and the sectors are basically the angles there. So what's the advantage now, for example, is there's a base station here and an A base station here. But within that set of channels that A has, the set of channels labeled 5 in this sector are the set of channels labeled 5 in this sector. And so these users over here won't get any interference from this base station because its transmissions on those channels are pointed in a different direction. So you sort of get greater reuse capabilities in this case. In this example, they are only using A's and B's to color all the channels. So the idea is that within each cell, you're further subdividing the populations. Here's a different picture of, this is a slightly different amount of sectors, though. Maybe this picture.
See, the above picture is only, if you see, onto the right.
This one?
Right?
This one?
Yeah, so you put it on, so you have the settings with the edges.
I think they're somewhat equivalent also because you can draw hexagons centered around these as well. So I think it depends how you draw the image to some extent. So here's, leave that out. So here's sort of another figure showing. So basically, this base station's sector over here would interfere only in this direction, right? And so if you space apart reuses of this channel sufficiently far away, it wouldn't cause as much interference. Okay, so to get back to our discussion here, can I have it back at the document camera, please? So this example we showed, and often what you see has these simple hexagons kind of shown. But what about sort of an arbitrary cellular system? So first of all, I should mention again, the channels can be anything. They can be frequencies, they can be codes, they can be time slots. And so long as you're reusing the same time slot and the same channel and the same code, but by sufficient distance, there won't be interference, right? So that's sort of the key idea. So if you have an arbitrary cellular system, things may not look as clean as hexagons. In fact, they may just look like really arbitrary amoeba-like shapes, right? That completely depends on the propagation characteristics of the environment, the power levels of the base stations, which may not all be uniform, maybe because of some interference reasons or regulation reasons, or even cost reasons. The company that's deploying the base stations might have a choice between equipment, some of which transmits at lower transmit powers than others, and for cost reasons, there's only a certain number of high transmission power base stations they want to invest in, and smaller, and others that are of different power levels, right? So there could be all kinds of reasons why the actual cellular propagation environment looks nothing like the beautiful cellular shape we just looked at, right? So that's more of a textbook picture. Reality looks often more like this. Okay. So when reality looks more like this, that simple, clean sectorization and channel allocation may not be the optimal solution. Right? In fact, may not even be possible to identify what the corresponding hexagonal shape would be for this. Okay. And so a different approach is called for, and one way in which people tackle the problem in real-world environments is to model the interference structure as a graph. Okay. So some of you might have taken CS570, or in other contexts, maybe in an earlier networking class, seen what we mean by graphs. Even 450, I think, does introduce the idea. But in general, just to recall, a graph is a description of two different sets, a set of vertices and a set of edges. Okay? So vertices, in this example, what we would want to do is make each cell a vertex. So if you have a set of cells, let's label those cells. And so in our example, the cells would be vertices. Then to define the graph, we need to put edges between vertices. And what we do is we say interfering cells have an edge between them. So in this particular case, let's try and draw what this graph might look like. So here you have a vertex for the cell A. You have a vertex for the cell B, and we can draw an edge between them because they're right next to each other. We can argue that they're likely to interfere with each other. If you use the same channels in A and B, there'd be too much interference. Similarly, if you have your node C that interferes with B but not A, you have some other node D which we can say interferes with B, with C, and with A. We have some node E, which is another cell that has certain edges between them. We have another node G over here, a node F. Maybe F interferes with all of these. What did I have? I have an H, an I, a K, okay. So we create here a graph in which there are vertices, vertices or nodes, and there are edges between them. Okay. So the edges basically represent the interference relationships. And now what we're asking, if you think about this just as a graph, is can we assign channels to these cells in such a way that interfering cells don't get the same channels? So in our earlier example, we were dividing the entire spectrum into 3 pieces. We labeled them ABC. Now I'm labeling the cells ABC. So we'll have to, let's use numbers, for example, for the sections of channels. So the question to ask would be, which set of channels do I assign to which cell, such that I don't have neighboring cells with interference. One big difference, unlike the hexagonal example we saw, is that things are not regular. So some cells might have a lot of neighboring cells, other cells might have fewer neighboring cells. So in general, the structure is not as regular as it was for the hexagon. And so that simple policy of coloring them the way we saw earlier may not always be possible. And in particular, it may not even be true that just breaking up my spectrum into 3 pieces will be enough. Okay, even that's not obvious. So the problem that we have here is sort of how many, let's call them sort of chunks, if you will, should the spectrum be divided into? That's one question. And to which chunk to allocate to which cell to ensure neighboring do not interfere. Okay. And just to clarify what we mean by do not interfere, we're really focused on the mobile user. So you're carrying your mobile phone in your pocket, you're close to some cell. It's using a set of channels, it's allocating some portion of the spectrum for communication with you. If the next base station over that's also relatively close to you is also using exactly the same channels, it's talking to some other user on that channel, it's going to show up as interference to you. You don't want that to happen. Right? Or maybe it's a CDMA system and these are codes we're talking about. You don't want the same code that's assigned to you to be also in use in the very next cell over there because its transmissions will start to bleed into your receptions. Right? And so that's the sense in which we want to make sure this interference doesn't happen. So, these are the questions that we want to solve. And what we do, and the reason we have converted from this cellular picture to a graph picture is that this particular problem that we're interested in solving is related to a well-known problem in graph theory that's called vertex coloring. Okay, sometimes people just call it graph coloring. But vertex coloring is a special case of graph coloring. So one thing that in this problem you're trying to do is you're trying to allocate a set of colors, okay, one to each node or vertex, so that no two vertices sharing an edge, have the same channel, have the same color. And minimize, and this part is key, minimize the number of colors used. Okay. So minimizing the number of colors used for our problem of dividing the spectrum into chunks is answering that first question in a minimal sense, in an optimal way. So we want to divide our total spectrum into as few chunks as possible. Why is that? Why is it good to break it up into fewer chunks? Because so the fewer the number of chunks, the more channels in each chunk, the more users that cell can support. Right? So this fewer chunks implies more spectrum per cell, okay, and which implies more capacity or users per cell. Okay. Of course, these days, as we're moving away from voice calls to data, primarily, it's not so much a direct one-to-one mapping between number of channels and number of users. It's just the more spectrum, the better, right? Because we're kind of sharing that spectrum. So if we want question. So if we want fewer chunks, which translates to minimizing the number of colors used, that's exactly this problem known as graph coloring. And the question is, how do you do this? If I give you any graph G, okay, that's the input to the problem, and the output of the problem is a set of colors I assign to all of these vertices, such that no two neighboring vertices will end up with the same color. And I want to make sure that the total number of colors I use is as few as possible. That's exactly what graph coloring does. This problem, vertex coloring, is NP hard. So what does that mean? Some of you might have seen this expression or even learned it in 570, but others may not. So let's spend a few minutes explaining this concept. So you've encountered certain graph algorithms already. So for example, if you look at Dijkstra's algorithm, that's a graph algorithm. Okay, it solves a particular problem on a graph. I give you a graph. In that case, we label all the edges with some distance, and I ask you what's the shortest path between point A to point B. What Dijkstra's algorithm does is it will take that graph, take the edge cost, and will return to you the answer. It will tell you this is the shortest path, okay, or Bellman-Ford, for example. How long it takes to run Dijkstra or Bellman-Ford will depend on the size of the graph that you feed it. Okay, and in that particular problem, how long it takes to run Dijkstra's or how long it takes to run Bellman-Ford is a polynomial function of the size of the graph. In other words, in fact, the exact one is, I think, cubic. Let me get the runtime. So, for example, okay, so some problems such as can be solved exactly in time that scales polynomially in the problem size. So example, if you take Dijkstra's, takes, we say, big O of V square, right? This is with a simple implementation. Okay, and it turns out if you do a much more careful implementation, in fact, you can even reduce it to something like this. V log V. More clever implementation. What does this mean? It means that if I double the size of the graph on which I ask you to compute the shortest path, you're going to find that it takes roughly 4 times as much time to compute the answer, in the worst case. It might be even quicker, but in the worst case, it doesn't scale more than that. If I have a graph that's 3 times as large, it might take you 9 times longer. So it is taking you longer and longer as I give you harder and harder problems. But somehow, that scaling is benign. It's sort of growing as a polynomial function. Polynomial functions in computation, if you have an algorithm that can do that, are considered efficient or tractable. Okay, so these problems are considered or efficiently solvable. And they belong to, in computer science terminology, they're said to be in the class of problems known as capital P. Okay. So they're all the problems for which there exists some algorithm that can solve it efficiently. And by efficiently, we just mean that how long it takes to solve the problem grows as some polynomial function of the size of the problem. For other problems, such as the longest path problem, there are no known polynomial time algorithms. What is longest path routing? I give you 2 nodes on a graph, and I ask you to find me the longest path that connects these 2 nodes. It turns out there is no algorithm anyone knows, unlike Dijkstra's for shortest path, that can guarantee that for every problem instance I give you, you can solve it in time that runs polynomially in the graph size. the best ways we can think of solving them today that are guaranteed to give you the right answer grow exponentially in the graph size. Right? They will grow something instead exact algorithms take exponential time. So what do we mean by exponential time is, something like 2 to the n, or 2 to the, where n is the number of nodes, or 2 to the v, let's say. Okay. So something that's where the v, this number of nodes in the graph is showing up in the exponent, is going to grow much, much faster. So then when I scale the size of my graph, solving this problem gets harder and harder and harder and harder. In fact, the longest path problem is very closely related to a well-known problem known as the traveling salesman problem. Okay. Or Hamiltonian path problem. In fact, this is called the Hamiltonian path problem. So this class of problems, we actually don't know if we can even solve them efficiently. In fact, the best conjecture as it stands today is that for a lot of these problems, there is no polynomial algorithm. But nobody's proved that yet. In fact, it's considered the most important open problem in computer science, is whether all of these problems for which we don't currently have polynomial solutions actually have a polynomial solution. I'm going to simplify the discussion here a little bit. It's not 570, so I want to talk about what does NP-complete mean, how to do reductions, how to prove, when does a problem have to be referred to as NP-hard as opposed to NP-complete, decision problems and all of that. So I'm not going to get into a lot of detail here. But the problem that we're interested in here, this one, where we want to allocate a set of colors, one to each vertex, so that no two vertices share an edge, and you minimize the total number of colors used. I give you a graph. We don't know today of any algorithm that can guarantee me an answer to this problem that can run in polynomial time. Right. So these problems are called NP-hard. So the problem that we're interested in vertex coloring is NP-hard. Okay? So I want you to have this thing to take away from the class, that not every problem has an efficient solution. Right? That you can guarantee with your algorithm, you take a problem instance, you'll give the answer quickly, and the answer will always be correct, no matter what input I had. We can relax two things here. So what it means for it to be NP-hard is, so this implies cannot guarantee exact solution quickly, always. Okay. So first of all, cannot guarantee the exact solution, cannot guarantee it quickly, and cannot guarantee it always. Right. So these are the things that are the consequence of a problem being NP-hard. But the thing is, we can sometimes relax pieces of this. So what you might be able to do is give an inexact solution quickly always. You might be able to give the exact solution quickly most of the time. You might be able to give the exact solution always, but not quickly. Does that make sense? So there are combinations of these that you can do, right? But not all three of them. Right? So there's sort of these three pieces to it. What it means for a problem to be NP-hard is that you can get all three of these together. But it does mean that you can get away with some pieces. And what actually happens for a lot of practical problems, for many, let's just say that, for many practical problems, okay, can use heuristics that are fast, okay, and often, right, not always, and this is important, often give exact optimal or near optimal solutions. So often this is the best we can hope for problems NP hard. So I cannot give you an algorithm like Dijkstra's that will always return the shortest path and will always be fast. But I can have an algorithm for graph coloring in this case that is a heuristic, will be fast, but is not always exact and is not always optimal, right? Sometimes is optimal, or many times is optimal, and sometimes is near optimal, and sometimes is not near optimal or exact.
Why do we want it? We are not going to calculate the graph coloring every time.
Yeah, so in this particular example for cellular, you might argue that you're willing to get solutions that are not fast. You might say, since I'm only going to do this maybe once a year, between upgrades to my installation, maybe I just need to solve this problem once a year. Maybe I'm willing to spend 3 weeks getting an answer, and then I can deploy that. And that's actually a valid point. In other settings, and we'll see, this idea is not just for cellular. It could also be applied to multi-hop networks, and you allocate channels to links rather than to cells. You might need to do this calculation very frequently because the topology might be changing very frequently. Even on the cellular example, if your traffic load changes, you might want to allocate different amounts of channels to different cells. Instead of allocating them all the same amount, then you can have a variant of this problem, but you might need to recalculate that depending on the load condition. So then you might need to do repetitions. Right. Right. So when you get into sort of dynamic channel allocation, then you need fast solutions as well. Okay. So this is one thing we can do, right? So you can, for many practical problems, not all of them, right? There are some problems that are so hard that even our best fast heuristics don't often give good solutions. They often give bad solutions. But for channel allocation, we tend to have at least one good heuristic that works like 90% of the time really well. So I'll describe that heuristic first, and then we'll look at other options as well. So that's what we're going to look for, is a heuristic algorithm for graph coloring, for graph vertex coloring. And it goes by different names, but one common name for it is, or at least the one we're going to use in our class, is called greedy vertex degree ordering. So it works as follows. So step 1, sort vertices in decreasing order of their degree. Okay. So in graph theory, the degree of a vertex is the number of edges that go out of it. Number of neighboring vertices. Right, so how many edges go out is how many neighbors you have. So from the top of this list, assign the earliest possible color, reusing if possible. So let me explain how this works, but this is the entire heuristic. There's not much more to it. So let's explain this heuristic by actually solving the example problem we started with. I'll try to redraw that graph. So there's A, there's B, C, D, E. Okay, so here's the graph that we had, cleaned up a little bit here. So we're going to, so the first thing the algorithm says to do, this greedy vertex degree ordering heuristic, sometimes I'll shorten this to just call it GVDO. What it says is we need to write them in sorted order. So who has the highest degree here? So let's kind of put numbers next to each node of how many edges it has going out. So A has 4, right? B has 3, C has 3, E has 4, D has 1, 2, 3, 4, 5, 6. G has 2, F has 1, 2, 3, 4, 1, 2, 3, 5. 1, 2, 3, 4, 5, yeah. 1, 2, 3, 1, 2, 3. So if we were to write them in sort of decreasing order, we would say D first, then I. Then we can break ties arbitrarily. We're just going to, in this case, I'll use alphabetic order, but it doesn't have to be. B, C, H, J, K, right? And then G. Is that everything? A, B, C, D, E, F, G, H, I, J, K. Yeah. So this is in order of their degree. This is the highest degree. This is the lowest degree. So this is the order in which we're going to start assigning colors to them. So we're going to assign them colors. I'm just going to give a certain set of colors to work with. Let's just work with, I don't know, the rainbow colors. Hopefully we won't need more than, actually I know we won't need more than that. So let's say we're just going to do violet, indigo, blue, green, yellow. Yeah, you might need more, but as we'll see, we won't. So the node with the highest degree should get the earliest color, okay, which in this case is violet. So we're going to assign this one V. What's the next one is I, which is this one. We want to assign it the earliest color, so maybe I should make it explicit here. So the earliest possible color, reusing it if possible, but the key point is that that does not violate the edge constraint, right? Remember, the constraint says that you can't assign a color if one of your neighbors already has that color. So in this case, the earliest color would be violet, but I can't assign that because that a neighbor has that. So given that, the earliest possible color for this one is indigo. So I gets I. The next one we should assign is node A over here. And the earliest possible color is violet, which is fine to allocate. No, it's not fine because it's got this interfering edge. The next possibility would be indigo. It's not possible. So the next one possible is B, blue. Then the next one in our list is E, which is this node over here. Now, it can be assigned violet, but it can actually be assigned indigo. So we see that reuse happening here naturally. Okay. So we are allowed to reuse so long as the current neighbors of this node are not already allocated this color. F, this node over here, cannot be allocated violet or indigo, but can be allocated blue. Node B over here cannot be allocated violet, but can be allocated indigo because indigo is not one of the neighbors right now. Okay. Then this node has neighbors that have indigo and violet, so it can be allocated blue. Node H over here has a neighbor that's indigo, a neighbor that's blue, but it doesn't have any neighbor currently that has violet, which is the earliest possible color. Then we have J, which cannot be allocated violet or indigo, but can be allocated blue. K cannot be allocated blue or indigo, but can be allocated violet. And G over here can be allocated violet. And we're done. Okay. So it only needed 3 colors So that's kind of remarkable if you think about it, because it wasn't like the hexagonal structure, so it wasn't quite so clean. It so happened that the way I drew that figure, we could still make do with just 3 colors. Right? It's not always 3, but in this example, it worked out. The algorithm is very simple. Right? What we don't have is a guarantee necessarily that the number of colors we ended up with was the lowest number of colors possible. That's the thing that we can't guarantee. But in practice, in fact, you can do better. In this particular graph, you can actually prove that there is no solution that could have done better than that. One way to see that is to look at these 3 nodes. And you can see that there's no way on Earth you could have allocated just 2 colors to these 3 nodes. Why is that? Because whatever 2 colors you allocated to any 2 of them, for the third one, it would have to be allocated the third. Right? So in fact, you couldn't have done better than 3. So on this particular graph, this is actually optimal. Right? And so this particular example, the heuristic gave us the optimal solution. However, as I said before, there's no guarantee that with this heuristic you'll get the lowest, always. But so what can we say? So the number of colors needed, so the optimal number of colors needed is called the chromatic number of a graph. So sort of chi g. What are some things we can say about chi g? Is it's always less than equal to so this is called the max degree of graph, and it's always bigger than another number, and I actually forgot what's the typical Greek letter we use for it, but let me just use psi here of g, where this is the maximum clique size of graph. Okay, so let me explain the left-hand side. So the clique is a set of vertices that are all connected, or subset, let's say, subset that are all connected to each other. In other words, a clique of size 1 is trivial, it's just one node. A clique of size 2 is just a link. A clique of size 3 is a triangle. A clique of size 4 would have to have all of these edges in it. A clique of size 5 would have all of these edges in it. Okay. And so on. So you look at the graph that you're given with. If you can find the largest clique in it, which the reason I picked out that particular example is that I don't see anything here that's a clique of size 4. I only see at most a clique of size 3. Okay, so here's a clique of size 3. All the triangles here are cliques of size 3. But if, for example, there had been, if this edge had existed between B and I, we would have had a clique of size 4 there. Okay. So whatever that clique is, like if you find the largest subgraph that is fully connected, that's the maximum clique, look at how many nodes are in that clique, you'll need at least that many colors. There's no way for you to do less than that. And the proof is very simple, right? We just looked at that. Because if any of the, fewer than that clique size number of colors is what you had, then there'll be one node which is going to conflict with all of those colors, and it's going to need its own color. Right? So that's why this is a lower bound. You can't do better than this. Okay. So if GVDO gives you a solution, gives you a certain number of colors, and you find that the number of colors it gives you matches this lower bound, you know you found the optimal, because the optimal cannot be less than that. Okay, so that's a way of testing your algorithm's output and telling that you got the optimal. On the other hand, sometimes it may not give you exactly this number. And if it does not give you this number, then the most you can tell is that at least you want to make sure whatever number it gives you is less than the upper bound, right? The upper bound is pretty loose. In many cases, you don't have the number of colors you need anywhere near this upper bound. So the upper bound in this case, the node with the maximum degree is node D, and that was 6. So 6 plus 1, 7 is like an upper bound on how many colors you might have needed. Okay. And here's how we can prove that GVDO will also satisfy that bound. Because whatever number, in the worst case, imagine some node in the graph. Okay, it's going to have a certain set of neighbors. Okay, this is a little bit more complicated than this, but roughly speaking, if you look at the set of all possible colors, whatever colors they've been assigned, you can always pick something, right, in the set of colors that does not conflict with them if you have at least the degree plus 1 number of colors to choose from. Like whatever colors they've been assigned from that, you can pick one that's not been assigned if you have that many colors to choose from. So this takes a little bit more thinking, but in fact you can prove that the GVDO heuristic will never take more than the upper bound. It may not match the lower bound, it may not even be optimal, but it's at least less than the upper bound. Okay. So, yeah, basically can show, this is not a trivial thing, but can show that GVDO never needs more than this many colors. But this bound could be loose. I mean, there are graphs on which this number is much higher than this number. Even already here, there's 7 versus 3, and you could have done it with 3, so the bound is kind of loose. Maybe a loose bound. So in the time we have remaining, I want to describe how the problem we just described is not just for solving channel allocation in cellular networks. In fact, it can be used for multi-hop wireless networks of any kind. In fact, we're using, sorry, I don't know what I just did here. Oh, this is some number there. 4. In fact, we're using this algorithm in doing channel allocation decisions for a test bed that we maintain at USC. So the idea is for allocating channels to links in multi-hop wireless networks. Such as low power IoT networks, and we'll talk more about these types of networks, or mobile ad hoc networks, or sometimes they go by wireless mesh networks. So the basic idea here is that you have a set of radios, and these radios have a link to each other. And so it's a multi-hop network, and you're trying to get data from any pair of node to any other pair of nodes, or in IoT, sometimes you're just trying to get it to a common sync node. And so you have, these are not cells, they're actually nodes. And these edges no longer represent interference, they actually represent communication links. So they're sort of wireless comm links. These are your radio nodes. Okay.
Excuse me, Professor, here's your 5-minute warning.
Okay. So what we are trying to do now is we're trying to allocate time slots or frequencies or codes to these links. Okay. And we still have constraints about which links can be allocated the same time slot or the same channel or the same code. So what might be a constraint? So one constraint you might have is that if I allocate a certain time slot to this link, I can't allocate the same time slot to, say, this link or this link. Maybe because it's using the same sender, and you can simultaneously be sending different messages to different nodes on the same time slot. A different kind of link interference might be that maybe I cannot send from A to B at the same time that I'm sending from C to D. Why is that? Maybe because while this is happening, if C was transmitting to D, B is close enough to C that it would hear the interfering transmission, and we're not doing power control now, so whatever power level you're at might be such that it actually causes interference. Okay. So in this case, this link and this link cannot be simultaneously activated, we're saying, right, because of interference from C to B. So whether it's because they're sharing a common radio or because they're interfering within each other because they're too close to each other, you might have reasons why certain links cannot be operated at the same time. So let's just say there's some link over here and this link A to B, and these are perfectly fine to operate together, maybe because, maybe not in this example. Let's take another link. Let's take G. Maybe this link and this link are sufficiently far apart that it's okay for them to be operated at the same time. There'll be no interference between them. But for the other pairs of links, there may be, if they're too close to each other, there may be concerns. So maybe A to E will interfere even with B to D, because if B is talking to D, it might interfere, at node A, and that might affect A's transmissions or something. Okay, so you might have reasons why certain pairs of links cannot be allocated at the same time. So what we do in order to convert this problem, so the goal is to need to allocate channels to links such that links that interfere are given different channels. So that's the problem we want to solve. So in order to do this, what we do is we convert it into something called a conflict graph. So this is our original graph G. We're going to create a conflict graph. We're going to call it H. And in the conflict graph, the node of H is a link in G. Okay, so the original graph G that we have here is a communication graph, because it tells us who can talk to whom. But in the conflict graph, what we're going to call a node are the links, because it's to the links in this example that I want to allocate a channel. Okay, and then the edges of H are pairs of links that cannot be operated on same channel. Okay, and so if I make this transformation, I will get a new graph H in which my nodes correspond to links in the original communication graph. Edges represent pairs of links that are not allowed to talk to each other. And over the conflict graph H, gives us the desired channel allocation. Okay, and again, fewer channels implies higher throughput. Or capacity per link. One way to think about that is that if those channels, for example, are time slots, if I imagine I have a frame of a certain size, if I break it up into 3 pieces versus I'd break it up into 10 pieces, in the case where I only break it up into 3 pieces, each of those pieces can be repeated more frequently. Right? Once every 3 time steps it shows up again. So my data rate is going to be higher if I'm breaking it up into a smaller number of pieces. Okay. Similarly, if I have sort of a spectrum broken up into chunks, or if I can allocate more channels to certain links, I can have a higher throughput. Right? So for the same reason as we were doing it for the cellular case, again, minimizing the number of colors is important. So the way to solve the problem is the same. We can use GVDO. Right? Can use GVDO for this. So it's a different problem. It's a completely different type of wireless network. It's not the cellular network, and we're not allocating channels to base stations. We're allocating channels to links. But the algorithmic solution is the same, because we can convert from the communication network, in this case, to a conflict graph, and then solve it. Really, what we did, even for the cellular, is we started with a cellular graph, and we converted it into a conflict graph. This graph is a conflict graph, because the nodes here represent, in this case, cells, but they represent objects to which you want to allocate the resource, and the edges represent conflict between them. You can't allocate the same resource to two neighboring ones. So long as you can do that, so in, for example, this picture, so we have all of these links. We have link AB, link AC, AE, EC, CD, BD, CB.
Excuse me, Professor, you're out of time.
Okay, so each of these links represents a possible node, so that's how many nodes we'll have in the conflict graph. So in the next class, I'll work out an example with this type of conflict graph, but that's sort of the key idea is still the same. All right, so we'll stop here.
This concludes EE 597 with Professor Krishnamachari on Wednesday, June 29, 2016.